All right, I'm surprised nobody asked. What's the difference between a jeweler and a cell biologist? A jeweler and a cell biologist. This one I have a feeling they got from like a highlights menu.
Okay. How they know of it.
What's the difference between a jeweler and a cell biologist? Actually, no, this is my oldest. I bet she did come up with this. One sells watches, and the other one watches cells. Alright. This one I know they made up. What kind of animal would you never play video games with?
A cheetah.
A cheetah. There you go. They are rather creative, aren't they? Their calculus questions are so boring, but their jokes are good. Okay. So, let's talk now, as we shift gears, we're going to talk some of the details about what we've laid out in the first part of the lecture. And what I want to talk about here is, what happens to autoreactive B cells. We talked about autoreactive T cells, but we haven't talked yet about autoreactive B cells. Remember, these are the cells that actually make antibodies. So you also wouldn't want to harbor a response against like your beta islet cells, but you also don't want to make antibodies against your own tissue. And there are certain circumstances where you'll make antibodies, and you can make antibodies that are actually stimulatory antibodies. And they'll stimulate a physiology that you don't want to have happen. Or they're blocking antibodies, and they bind to the receptor, and they prevent the receptor from actually responding. And so we'll see that take place in different examples after the exam. But in the autoreactive B cells, we go through only central tolerance. So B cells, central tolerance happens in the bone marrow. So the way to remember this is T cells thymus, TT, and B cells bone marrow, BB. Okay? Kids and I play this game. When you, I don't know, does anybody play this game? You drive around, you see a license plate, and if it's double three, it's like, you go double three, and you have to hit them. And then you do like double T. We did slug bug, but that got boring. So now it's, you're looking for double letters or double numbers. So double B's would be bone marrow B cells. Double T's would be thymus for T cells. Okay? So remember that little game. When you're driving around town, you see a double B, you're like bone marrow B cells, okay? Okay? But you have to hit somebody. That's part of the game. That's what's dangerous when you're driving, because they're all trying to dodge me, and I'm reaching back and trying to hit somebody so I can claim the double B. All right. So only central tolerance. I can't believe I have such a random thought. It might help you. So the central tolerance is the only mechanism we have with B cells. We don't have a peripheral tolerance. So we only go through apoptosis here, and if they're autoreactive, we'll kill them off through apoptosis. It's programmed for death. So we'll recycle their parts, and we'll try again. We'll try again. 90% of all the B cells that we make undergo apoptosis. It was 95% for T cells. It's 90% for B cells. So again, not a very efficient process, but we kind of already talked about why we want to do it that way. Now, if we're talking about antibodies, and we want to talk about how they combat antigens, we can look at a couple of different ways they can achieve this successfully. I had to adjust this video. It's kind of causing me challenges today. All right. How do they combat antigens? Well, we can look at things known as direct effects or other things called indirect effects. And it's just like what you expect. If it's a direct effect, it's going to be things like neutralization, agglutination, or precipitation. So what does that mean? Well, neutralization is it's going to bind and inactivate, or it blocks the toxicity, neutralizes it. So the antibody binds, renders it ineffective, the antigen. If it's agglutination, it causes the antigen that's already insoluble, so you have particulates floating around, and it causes it to clump, agglutination. If it clumps up, now it cannot travel into lots of different locations and cause more problems. The third direct effect of how antibodies combat antigens is with precipitation. So one modality for an antibody to travel throughout the bloodstream is to be soluble in blood. And so if you precipitate it out, it keeps it from traveling around. So precipitation making it something that's soluble, something insoluble. And then the indirect effects are exactly that. They're not targeted towards the antibody per se, or the antigen per se. They do something utilizing another pathway, another mechanism. So opsonization that I've talked about a few times today, this is actually getting the microbe ready to be phagocytosed. So you can see opsonization and phagocytosis in this top picture. You can see that here is the cell that is opsonized. You have activation via complement as your secondary signal, your costimulation, causing the phagocyte to engulf this particular entire cell, and now it's going to, through respiratory burst mechanisms, digest it inside. And then another indirect effect that we learned about 2 weeks ago pretty actively is inflammation. So antibodies can be manufactured by B cells, and those B cells could actually stimulate an antibody production that utilizes our second line of defense, which is inflammation. And you can see here with these two sort of arrows, our opsonization and phagocytosis example at the top, our complement mediated inflammation on the bottom. Okay, so now we get to the memory part. We've already seen the antigen. We've developed antibodies for it, whether it's IgA or IgG or IgM. The first time that we do that, IgM dominates. And then afterwards, IgM kind of subsides. You get some class switching, remember that? And then you have lots of IgG. And that should make sense because IgG is found where? In the blood. That's the one that's 80 to 85% of our circulating IgG. It's the one that crosses the placenta. That's the one that's found in breast milk, for that conversation at the break. And this response initially takes about 3 to 5 days, and now you have appropriate levels of antibodies circulating around bloodstream. Now, the second response is kind of the key one. So the second response, the IgM levels are about the same they were the first time, but the IgG is about 4-fold greater than the initial response. And the time, it doesn't take 3 to 5 days. It happens just like that. It's instantaneous. And so if anybody's had a vaccination to chickenpox, somebody on campus did it, because did you guys see that? Yeah. So we got this email that, I was like, oh man, I should invite that person to class and use them on a slide as an example. But that's probably not appropriate, so we won't do that. But we'll just talk about the example. So if you had the chickenpox vaccine, right, the antigen to chickenpox is something that you were exposed to, but it was an inoperable antigen. It's not going to cause chickenpox, but what it does is it causes your body to manufacture antibodies towards chickenpox. Okay? So the next time you're exposed to chickenpox, like this year in 2015 in the fall, if that's your roommate or on your floor, if you've had the chickenpox vaccine, then you don't have anything to worry about, because as soon as you see it, you're going to have an immediate response and you're immunized. Okay? So the second response is immediate and doesn't require time for it to take place. So a little bit of history on vaccinations. The first vaccine wasn't chickenpox, it was actually smallpox in 1796. So smallpox is an extremely contagious and deadly virus. It was really scary back then because in the late 1700s, we didn't really know much about this. Okay, there was no PowerPoint for us to show what an antibody looked like. So this physician named Edward Jenner, he made an observation that young women who were milkmaids, milking cows, would typically catch cowpox. But they were not ever catching smallpox, even when family members in their house had smallpox. So he thought maybe that something about cowpox was making them not susceptible to getting smallpox. So he had an idea that he decided to test on his patients. He infected purposefully his patients with cowpox, and they developed memory B cells. Now we know what they are. He didn't call it that. And then, what's even more amazing, this is the practice of medicine, folks, is he exposed those patients later to smallpox. This is a deadly virus, okay? He didn't really know how it worked, but it totally worked, okay? And we now know that cowpox and smallpox have very similar antigens with similar shapes. And so the antibodies that they develop work back and forth. It's just like the red cap can go onto the green marker and drive you insane, right? That actually works. So that's kind of the same idea of how cowpox and smallpox vaccination was discovered. So after this discovery, everybody was vaccinated against smallpox using a cowpox derivative. And it was so successful that in 1979, smallpox has been eradicated. Like the only existing ones are in the Center for Disease Control in a freezer. Okay? And so you know somebody that's their age, if they were being vaccinated as a kid, much like before the 70s, or if they came from another country, because it was eradicated more in Western countries first, they have a cowpox mark, usually on their shoulder, that looks like a really big chickenpox scar. It's about that large, and it's usually on the shoulder, and that's the vaccination. So vaccinations come from Dr. Jenner because vacca in Latin means what? Cow. Okay? All right. So cell-mediated immunity. Let's move on from B cells to T cells. And we're kind of wrapping things up today. Just a hint, when you only see like 25 to 28 slides for a 2-hour lecture, it doesn't mean we're getting out early. It just means there's a lot of material on each slide. Okay? So, cell-mediated immunity. Backing up, this is another picture of the thymus that we talked about in the first lecture of today. T-cell clonal diversity, right? This is that terminology we use to say that the immune system is going to be extremely creative about the different variants that it wants to generate to try to anticipate all the different things that it might actually come across. So this happens in the thymus, this clonal diversity. And in fact, there's a drug, or not a drug, but a hormone that's released called thymopoietin. And thymopoietin is released by the thymus to stimulate the maturation of these T cells. And through the central tolerance mechanism, we test them to see if they're going to be reactive, autoreactive. And we looked at that. We looked at these mechanisms where here is this proliferation phase. There's the entry of the T cell precursors to the thymus for T cell development. And these cells come from where? The bone marrow. So you might want to write bone marrow, and that's where these cells come from. Remember, if it's the bone marrow, remember it's the BB game, and they're B cells, they stay in the bone marrow, and that's where they become centrally tolerant. But if they're T cells, they go to the thymus, and this is where they go through central tolerance. And if they're autoreactive, bless you, they actually are stimulated for apoptosis. But the cells that make it out, ideally, are non-self-reactive. And if they are, we have some peripheral tolerance mechanisms that we can actually use, and we already described that. Okay, so our next couple of slides are going back to some of these earlier, this earlier diagram that I showed you, and I told you we'd come back to it, so here we are. The antigen presenting cells can present to different types of things. So if it's a dendritic cell, oftentimes, but not exclusively, oftentimes it presents to CD4 positive T cells. So these are going to be MHC class 2. They migrate to the lymph node. This is the lymph node, so they come into the lymph node. And in the lymph node, they're going to interact with these CD4 positive T cells right here. Once they become reactive and stimulated, these T cells are considered effector T cells. So you might have read in the textbook effector T cells. And there are different subtypes of effector T cells, also called helper T cells. So the subtype that we're seeing right here is Th1. That's a T helper effector cell, subclass 1. There are Th2s as well. We're going to kind of primarily talk about the Th1s. And these effector T cells, these CD4 positive T cells, get into the circulation and they migrate. And then they get out into the periphery and they can interact with a phagocyte that has found an antigen that they've been educated to respond to. And they start releasing cytokines, the helper T cells. Remember, the helper T cells don't kill anything on their own. They're just helpers. So they release cytokines, they blow the whistle. They are the true whistleblowers, the helper T cells. They blow the whistle, that stimulates an inflammatory response to migrate out of the blood system and bring in more macrophages to kill. Okay? And these macrophages ingest the microbes, and now you render it ineffective. The other pathway that the dendritic cell, in some cases, can migrate over here to the CD8 pathway. So in the CD8 pathway, the dendritic cell has the antigen. It shows it to the CD8 T cell. This is in the lymph node. The CD8 T cell becomes effective or activated, and we call it now a cytotoxic T lymphocyte. CTLs. Cytotoxic T lymphocyte. And this cytotoxic T lymphocyte migrates also into the bloodstream, and it moves over into the tissue. And this guy, unlike the helper T cells, this guy directly attacks the cell that has that antigen being exposed and kills it. Okay, we'll talk about how it does that here in a second.
Can you repeat what you said makes them effector T cells?
What makes them effector T cells is when they're activated by being exposed to an antigen. Okay?
So our MHC class 1 only involved with CD8, but MHC class 2 are involved with both CD4 and CD8?
No, so MHC class 1 is CD8, MHC class 2 is CD4. If the dendritic cell presents over to the CD8, this is a MHC class 1 pathway that's being used. That's a good question. This does kind of make it seem a little confusing. So it is very consistent of CD8, MHC class 1, CD4, MHC class 2. So if you memorize that relationship, that would be a good thing, because it won't change. Okay. Now I want to draw your attention to this box, okay? And what's going on in this box? The next slide is the same diagram, just different information. And this is walking you through what we just talked about with CD4, okay? Then walking you through with what happened with CD8, just like I did on this next slide. So this is all the language that I just talked about. But the one thing I haven't talked about is this IL-2 costimulation, which is this inset right here. So if you look at this, this is a step between when it's being shown the antigen to when it's effective, cytotoxic T lymphocyte. And you can see here's the antigen-presenting cell. We call this the naive T cell. Naive because it hasn't seen the antigen yet. It is exposed to the antigen, and then what happens is it releases IL-2. Interleukin-2 binds to this interleukin-2 receptor. And for the cytotoxic T lymphocyte, this interleukin-2 pathway is in fact the co-stimulation event that we were talking about with the CD4 before and with the B cells before. So all of them have their own co-stimulation event. CD8 positive T cells utilize interleukin to do this. And when this event happens, this is where you get your effector T cells. To answer your question earlier, when are they considered effector? With CD8 positive T cells, they're effector after the interleukin co-stimulation. And they also start manufacturing simultaneously your memory T cells. So the next time you're exposed to that antigen, again, the response is faster.
Am I right in thinking like these naive T cells find the antigen somewhere in the body and then they go back to the thymus for to be
No,
effective?
no, typically the antigen presenting cell finds it somewhere in the body.
Oh, okay.
It moves to the lymph node. That's where the T cells are hanging out. It shows it. Look at what I found. Right, T cells are sitting on the couch eating potato chips. And the worker bees, the antigen presenting cells, find it, make their way through the lymphatic circulation to the lymph nodes. Have you ever wondered in 202, like, what's the whole point of the lymphatics? Right? It's like, it seems like I get the veins, but because you don't spend a lot of immunology time in 202 on the lymphatics. The lymphatics is this fluid flow that's alongside the bloodstream that's allowing your lymphocytes to circulate throughout your entire body. Does that make sense?
I just didn't know if they had to mature in the thymus or if they can do that in the lymph.
No, they mature in the thymus, but they're considered naive.
Okay.
It's like they're educated, but they have no real-world experience.
Okay.
You guys understand what that means? Like, I know all the answers. I can find everything in the textbook. But what kind of job experience do you have? Well, none. Okay. Well, I'm looking for somebody who experienced. I know, but I don't have any. I need to get the rest of that catch-22. So it's like they have all of the knowledge, but they have no practical experience yet. And that happens in the lymph node.
So the central and peripheral tolerance happens for the naive T cells.
Yes.
Okay.
Yes. So they're still naive after they're tolerant.
Okay.
And they're only now effector once they've been exposed to an antigen. Okay? Steven? It's only autocrine. The interleukin-2 pathway is an autocrine co-stimulation event. That's a really good question because I didn't mention that. Okay. So now with the CD8 pathway, we've created them in the bone marrow to the thymus. Now they become centrally tolerant. They're not self-reactive. They're exposed to an antigen, makes them a cytotoxic T lymphocyte. Now they're effective, and they're cruising out and they find what they're looking for, right? Because they were trained to go kill this antigen. Anything with this antigen destroyed, how do they do that? So they get here, and they go through this process known as cytolysis, or cytolysis. They lyse the cell using two main mechanisms. And the exact pathways I don't care as much about, and that's why it's very generic. I just want you to understand that there's either an extrinsic way, where they basically insert a perforin in a granzyme, and through caspases cause an apoptotic mechanism, or intrinsically, the Fas-L inside the cell binds to Fas, and that triggers apoptosis. And as apoptosis happens, it actually, in this case, lyses the cell, which is a little bit unusual for apoptosis. Because we've always learned up to this point that apoptosis kind of sends out these little blebs. So that does happen here, but the cell at some point is lysed and completely rendered dead. Okay? Only cytotoxic T lymphocytes are doing this. Now the memory cells on cytotoxic T cells, or just T cells in general, rather. We talked about memory Bs, right? We talked about vaccinations, right? So I want you to say that next time you go to the doctor. I'm ready for my vaccination. Right? Are you Dr. Jenner, by the way? See what your physician says. We'll see if they know who Dr. Jenner was. Wouldn't that be interesting? Maybe you could educate them on who Dr. Jenner was, because all doctors love to be educated like that. Your copay might be 2x that day, but that's okay. All right, so memory T cells. Memory T cells have become experienced, right? They're not naive. They have the experience. They have real-world experience. They've been out in the battlefield because they've had a previous antigen exposure. So a lot of times we'll call this an antigen-experienced T cell. The second encounter is stronger and faster, just like what we saw with the B cells. And we've got sort of this complicated diagram here, but let me just walk you through. Here's our naive population. Here's our effector cells, and this is the language that we keep coming back to. When do they become effector cells? Once they've been exposed and they're no longer naive to the antigen. And in the case of cytotoxic T lymphocytes, they're going to trigger these things for apoptotic death and lysis. And when they are exposed, you generate both central memory cells and effector memory cells. These guys stay within the lymph node. And in fact, the ones that stay in the lymph node, you can tag them for CD cluster 62L, CCR7, or IL7R. All of these surface expressing labels will tell you that it's a central memory T cell. So you'll only find those in the lymph node. The ones that are cruising around, which we call tissue homing, are the effector memory T cells that are actually outside of the lymph node. And so you have them in both locations, which makes sense. You're inevitably going to see them the second time in the lymph node through the lymphatics as things return back to the blood supply. But you may actually run into them in the circulation. So you want to find them in the tissue. And so you can see the counterparts of the CD62L is the low version of that. So the low and the high, these are the ones that discriminate tissue versus lymph. The IL7R is the same in both. Okay? So there are two different populations of these memory T cells as we get out into the second response. Okay, it kind of wraps up the new material. So I want to kind of get us ready for the exam with a couple of practice questions. Okay? So these are not post-quiz style, because you're not going to have the internet. You don't have the internet on your exam next week. You don't have your book. It's all what's up in here. So I really want to encourage you to focus on the lectures, because that's where I'm going to write my questions. The post-quiz this week is going to have a zinger. You'll be like, oh. Okay, you're going to have to look it up. It's the outside-the-box one. But these ones are examples. Okay, so which is not a correct pairing? CD4, helper T cell, CD8, MHC1, CD4, MHC2. This is for you back there. Plasma cell antibody, or APC, antigen-presenting cell fibroblasts. E. Antigen-presenting cell fibroblasts. Why? What are the antigen-presenting cells that we talked about? Dendritic cells, macrophages, B cells, and we said a subclass of dendritic meaning Langerhans cells, but that's really kind of the same thing. So a fibroblast is not a classic antigen-presenting cell. After degranulation, mast cells release prostaglandins and leukotrienes that perform which of the following functions? Go ahead and read it. If you have an answer, raise your hand. After degranulation, mast cells release prostaglandins and leukotrienes which perform which of the following functions? So prostaglandins and leukotrienes, we talked about those in which lecture? Inflammation. It was one of the mechanistic slides. And both of these are derived or manufactured from what? Arachidonic acid. Remember that word? And arachidonic acid comes from where? From where it starts. You would be right. From the phospholipid bilayer. You remember this slide? It was like it started here and it had like all these arrows kind of coming down to some like salmon pink or salmon orange boxes. Okay? What is it? Is it A? It is A. Why? Those are things that happen with inflammation. That's a really good guess. But if you look at that slide, vasodilation and vascular permeability were some of the results of leukotrienes and prostaglandins. Okay? So that slide obviously is one that would be wise to study. That's the hint. Right? Iridian's like, Okay? So, you know, they don't really have anything to do with the attraction of CD8 cells. They are not involved in the activation of the complement cascade, right? That's the kinin cascade. Opsonation of bacteria, D, they don't have any role there. So, you know, and it's not three of them, it's only answer A. All right, this is another one. Which type of necrosis do you receive as a result of the glomerulonephritis? So I'm giving you some examples here. This is a normal glomerulus, right? And for those of you that don't remember 202, where would the glomerulus be found? In the kidney. Thank you very much. Okay? So this is a normal glomerulus. This is acute nephrotic something, right? This is glomerulonephritis. This is the diagram. Here is the corresponding histology. Right? Corresponding histology. Ooh, that looks pretty good. Right at the end of the lecture, it started to hit. And so you can see inflammation with the glomerulonephritis. And so if we're going to get a necrotic response, what type of necrosis would we expect in the kidney? Coagulative, caseous, fat, gangrene, liquefaction. How many of you think E, liquefaction? Raise your hand. How many of you think gangrene? Fat necrosis, caseous necrosis, coagulative. All right, the coagulatives have it. Why? Why is it coagulative? Because it's found in organs like the kidney, heart, the spleen, right? Pancreas. It follows the vascular tree, and it leads to this wedge-like appearance. Very good. Okay. In an experiment, enterobacteria organisms are added to the solution containing leukocytes. Engulfment and phagocytosis of the microbes is observed to occur. Next, you add a substance which enhances the engulfment. So which of the following substances is most likely to produce that said effect? A, complement C3b, glutathione peroxidase, immunoglobulin E or IgE, affectionately, P-selectin or NADPH oxidase. Complement C3b, right? Complement C3b, manufactured in the liver, circulates in the blood plasma. This helps to facilitate engulfment and phagocytosis. We actually talked about that today. Okay, here's our last review question, and I'll let you guys go. 9-year-old girl sustains a small 0.5 centimeter long laceration to her right index finger while playing Queen of Swords with a letter opener. Okay, this has actually happened. Which of the following substances on contact with the injured vascular basement membrane activates both the coagulation sequence and the kinin system simultaneously? Doesn't say that, but it's saying both, as an initial response to this injury. Thromboxane, plasmin, platelet activating factor, Hagman factor, histamine. How many of you say A, thromboxane? How many of you say B, plasmin? This is where clickers, pull your clickers out. How many of you see PAF, platelet activating factor? How many of you like Hagman factor? A couple like half masters, right? I'm not really going to go for it. Histamine? Okay, you guys like histamine? Okay. So the Hagman factor is the correct answer. It's also referred to as factor what? 12. Thank you. Very good. This is another one of those slides that's sitting next to the prostacyclins, prostaglandins slide. I would study that one too. Yes. Okay? Any questions from today? All right. We're done a minute early, but I'll let you go.